I never went back.
Huh?
I never went back to
You never went back to
I
this?
was not sure back today. I'm sure.
Now you're rocking the performative nails.
Well, I already had it. I just don't ever use them.
Where's your mantra? I think you forgot your tote bag too.
Huh?
You forgot your tote bag too.
That's already. There's that.
The guy that went.
I don't know. I saw him, but then I just stopped seeing him. Did you find out?
The one that got his bag stolen.
It's bad.
He was in your country. Howard.
Oh, wait, no, I'm in physics.
Okay. What is that? I had chemistry last semester.
Yeah.
Sure. The one that's right behind you.
I don't even remember anyone. I never asked for his name.
Yeah. I think I was talking to Jeffrey and he was telling me about like he started dropping
I
names.
think it was Jeffrey.
Jefferson, I mean,
Never mind, never mind, never mind that.
Jeffrey was telling me about people in our physics class and started dropping names that I didn't know. I know my lab partners, some of the people that sit behind me, some of the people that sit next to me, and like one person. Everyone else is an unnamed NPC. Oh my gosh. It's 4:20. It's 4:20.
So this question really is to review the formula that we had for polar curves. It's the range. You have to remember the right range. Yeah, I think you were using the wrong range. It's not 0 to. Yeah, it should be 0 to 2. 0 to. Let's look at the range. I mean, some of them are from 0 to 2 pi, some of them are 0 to pi. And we can quickly graph it to see what it is. The curve is sine 3 theta. It's a 3-petal leaf. So the common range will be 0 to pi or 0 to 1 pi. And you can kind of trace it. R equal to R equals sine 3 theta. So this is how it looks like. And this will see if you go from 0 to pi. So that's already the full thing. But of course, if you go from 0 to the small range, pi over 6, you draw half of the petal. And that means if you go from 0 to pi over 3, it's 1 petal. And you increase this figure to pi over 4, that's smaller. Pi over 3 will make a figure of 2 pi, 3 pi over 4. That's 3/4 pi. You can see if you finish a whole thing, which if you take whole shape. If you have 0 to 2 pi, of course, it's repeat itself. So basically, the right range, I think we should use is 0 to pi. So we would use the formula. This formula is for the area calculation. That formula is for the length. So you can see these two are using the wrong formula because it's really using the length formula in the root part. So the right one should be this one for the area calculation, 1/2 R squared d theta. And then we realize the A and B are identical. But the right range should be 0 to pi instead of 0 to 2 pi. So I think the right choice should be A. Because for the odd number panel, it's a three petal rows petal. If you have an even number of like C R equal to sine 2 theta. Then we have the petal are doubled, 2 double is 4. In this, you have to go from 0 to 2 pi. 0 to 2 pi to have the full shape. If you only have 0 to pi, it only draw half of it. So then if you want to draw the number petal is more, and you have to use a bigger angle. So for all the even number multiplied by angle in sine or cosine, you always have to use 0 to 2 pi. But for the odd number one, then a 0 to pi is enough to have all the petal traced in the curve. So the answer should be A, because we are not going the full circle 0 to 2 pi. It's not necessary to have that. So this question to identify, calculate area within the polar curve, we should be using 1/2 r squared d theta. And make sure you are using the right range. The range for odd number theta, it should be 0 to pi. For even number theta in sine or cosine, the range should be 0 to 2 pi. It should be A. Yeah. And that was the example on calculating the area within the full curve. Any questions? This is not a calculation question. We'll just set up the calculation. It's just to identify the right formula. Do you have any homework question you want to talk about? Are we getting more homework done over the weekend? Okay. So we're doing okay? Right, let me know if you have any questions. All right, so we pretty much finished what we planned for 10.1. I posted a homework for 10.1. Which basically are determining the right graph. Online, define the homework. But the main thing is try to finish your chapter 9. If you haven't finished your chapter 9, you can wait a little bit to pretend the class recording will be online, so you can watch the recording later to catch up if you're behind. But in the meantime, continue with chapter 10. Some of the work are trying to, when we were talking about wording of the surface, in 3-dimensional coordinate systems, every equation is representing a surface. Each equation, simple equation or really difficult equation, like equation given with x equal to 0, it's representing a plane because it's a degree 1 equation in variable x. X equal to 5 is a plane, y equal to 2 is a plane, x plus y equal to 1 is a plane. Whenever you are using the equation of degree 1, you are representing a surface of a plane. Now, in this question, we see a couple of different terms, and let's try to identify them next. For example, A has y squared plus z squared equal to r squared. I realize this equation has no x value. So it's a cylinder parallel to the x-axis. So this one is a cylinder parallel to the x-axis. Because it's a cylinder, we need to know its direction. The x-axis will be the direction. The cylinder opening along the x-axis. So that's the I was gonna try to match them. It's not a match. It's individual. So this is totally random. You might have a different set of questions in mind. A, describing the set of points whose distance from the axis equal to distance from xy plane. So distance from the xy plane by that equation. The That was the last question on homework. So how do we represent distance from the XY plane? It will be the absolute value of Z, right, XY plane. Okay, so the value, that's the distance. Now the other distance, the distance from the Z-axis, distance from Z-axis is, so then you'll be drawing whatever point that is, you are trying to connect to the Z-axis, and the distance represented by x squared plus y squared. Remember, a revolution about Z-axis will be r equal to x squared plus y squared. So this calculation is root of x squared plus y squared. And now it's this distance, and since they're equal, so we're setting these to equal, right? And then we square both side equation that give you x squared plus y squared equal to z squared. So that will be the equation representing this this surface. So what it is really, and you have what's called a circular relation between x and y, and then we have, I think it's also I think it was a cone, right? There's it's a equation of a line. If x equal to 0, then you have y equal to z, or y equal to negative z. Then if the z equal to 0, that's x equal to 0, y equal to 0. If we have y equal to 0, then x squared equal to z squared. So x equal to z or x equal to negative z. So the cone. So this is the equation of a cone, and then we want to look at where it's open. It would look like this. X, y, and that was z. So it's a cone this direction. Okay. You see the distance to the z-axis is this, and the distance to the xy plane is this. The distance to the z-axis is this. So it basically says this equal to this. So just saying the angle in the cone is this is 45 degrees. It's a 45-degree cone. Right, so we would say the cone open to the z-axis. So it would be D. Hope I didn't make it actually complicated. Are we okay? This is that one, and you can see the other scenario. It could be a cone opening. Like for example, a cone opening in the along the axis would look like y squared plus z squared equal to x squared. That's a cone. Now a cylinder opening along the x-axis will be kind of like, just making an example. And a cylinder facing x-axis will be a cylinder, so you could have a y squared plus z equal to 1. Since there's no x-axis, will be a cylinder opening along the x-axis, but it's a parabolic cylinder. If you want a circular cylinder, you have to do y squared plus z squared equal to 1 or equal to any other number. So that's the A kind of graph. But anyway, the graph that we see in part A would be D. All right, the second question, find the equation of set point for distance from z-axis equal to distance from x. So I guess the two questions asking for the same thing. I already was writing down the equation, this one, so we go for the one that's identical to me. So it's z squared equal to x squared plus y squared. So I think we all getting this different question, like a randomized question. For mine, the A and B seems to be asking the same surface. I'm not sure if yours is identical. So that's question 7. So we're using a kind of review a little bit what we did last week. The question was asking to match the graph, 3-dimensional graph. So it's the drawing picture using 2-dimensional image to represent 3-dimensional picture of it. So let's see. You can see the number 2, number 3, and number number one, number two, and number three. These are equation of a plane that goes on flat. Visually, the number three looks like a curved surface, but it's positive. So you have to have a positive z value for that. You can see z is a vertical axis, all pointers on top, and there's nothing below the xy plane. So you have to have a curved surface that's two-dimensional, but is along the z-axis. So I would say z equal to 2 plus, that one is number three. And then this one, number two, the number two, you can see the y-axis is parallel to the plane. This one, you see, it has intersection with x-axis and z-axis. There's no intersection with y-axis. We okay? So it should be equation linearly equal one in x and z, but no variable in y. And we can kind of see which equation represent that. There's a z, there's x, and it's negative in relation. So it's this one. It's number two. The number two is a plane that has no y-axis. Now z equal to -2 is a the e. Z equal to -2 is when the z value, and so it should be a horizontal plane at z equal to -2. And we don't see any plane that is parallel to the z. So we would say no on the graph. This one, c and z equal to -2 times x squared plus y squared. Then x squared plus y squared is positive. We multiply by -2. That means that z is entirely negative. So it's both up and down, right? It should have a negative z value in this graph, right? And none of the picture have any curve, and kind of already think the number three is a anyway. So we don't have that kind of graph there. All right, so that leaves us only two of these, and then we have these two images of number one and number four. Which one is it? We kind of have to compare. So let's focus on question one, picture one. So we copy that. Once we determine one of these, the other one, of course, will be a remaining choice. So you look at it. This graph has clearly intersection at z, the axis, intersection on z. It has a negative intersection on the x. They also have a positive, there is the x and the y is positive. So when you align all the other variable equals 0, you can identify the x, y, z intersection. So we're gonna find intersection, for example, for this, right? Let's try to find the intersection with the x's. When x equal to 0, y equal to 0, and you can see what happened if x equal to 0, y equal to 0, z equal to 2. So that seems to be make sense. I mean, this one is higher on the z, so z equal to 2. So that's a 0, 0, 2. And let's see the x. If z equal to 0, y equal to 0. Look at that equation. If z equal to 0 is 0 equal to 2 plus x, and then the y equal to 0, then we don't have to subtract to y equal to 0. So from here you get x equal to -2. Right? That seems to make sense if we get that -2. Because the x-axis is opening this direction. So that was obviously a negative x. And it's also following our right-hand rule, you know, x and then y. And when you curl crossing, like preventing crossing the x and the axis. Hope it's okay. We just try to identify. I'm just saying the axis is not going that way. It's going this way. We know where the x is supposed to be positive, where it's negative. We know that this is a negative x value. So that one was okay. And then let's make x equal to 0, z equal to 0, x equal to 0, and see what happens with y. The same equation if x equal to z equal to 0, x equal to 0 equal to 2, plus 0 minus 2y, and we see what happens to y. You solve it at y equal to 1, and that seems to make sense. So I would say this is definitely number 1 there. Okay, so kind of you see the points that you observe, the point of intersection you observe in the picture is agreeing with what indicated by the equation of the equation of plane. So this is number 1. And there are 1, 2, 3, then the other one must be number 4. And it's this one. You can also see the intersection. There's a positive x intersection, negative y, and positive z. And this one, it's the same thing. If x equals to 0, y equals to 0, z is positive. So it is a positive z intersection, and it's indicating a negative y. You can see if x equal to 0 and then z equals 0, then we have 2 plus 2y. So the intersection, the y value, when x equal to 0, z equal to 0, the y equal to negative 1, which is there. So that's kind of a major difference between the two images. Are we okay? So we're trying to observe useful information from the image, which allows you to identify which equation matches which picture. So this is the number 6. Any other one, let's match the name. The first one is, you can see between x and y is y squared minus x squared. I mean, the first equation. So x and y is hyperbolic relation. Are we okay? And then the x and z is parabolic relation because one square, one's not square. And then the z and y is also parabolic, meaning that if x equals 0, then you have z equal to y squared. So it's a parabola in the yz curve, in yz plane. Are we okay? So then the one that has only one pair is a hyperbola, and then there's 2 parabolas, so it's a hyperbolic paraboloid because the parabola has 2 pair relation. I'm just looking at variable pair by pairs. Are we okay? So we're trying to name them based on the relation between the variable, based on the look appearance of the equation. So that is a hyperbolic paraboloid. We would answer B. The second function, do you think what it look like? What's the name for the second one? Yes? Well, have you guys did this one? It's like square, add another square is an elliptical relation. So it's basically an elliptical relation between any 2 pair of variable. That's ellipsoid. Right, in this one, right, number 3, how do we name the equation 3? It's there's no z, right? So it has to be a cylinder, right? So it's what kind of cylinder? We have x squared plus y squared. So circular cylinder. Yes, thank you. So it's a circular cylinder. We answer D. Now, what about number 4? So degree 1, right? When all the variables is degree 1, it is a plane. Yes. It's what kind of plane? It's not horizontal, so we would answer that. The number 7 z equal to 4 is the horizontal because you have a vertical coordinate. What we use, assuming z is a vertical coordinate, so it's a vertical coordinate that equal to 4. So G is a horizontal plane, and that leaves these two. This one between x and y is elliptical because coefficient is 2 and 3. They don't have identical coefficient, therefore it's not circular relations between x and y is elliptical. And then between z and x is hyperbola. Between y and z is hyperbola. So it is an elliptical parabola. It's parabolic, right? Sorry, did I see the wrong word? So elliptical paraboloid. Basically, out of all the 3 conic sections, we kind of named them. So elliptical parabola is A. And this one, between z and x it's square with another one not square, so parabola if it's two-dimensional, but it's paraboloid, but it's, no. It's parabolic relation between z and x, but there's no y variable, so it's a cylinder. So this is the parabolic cylinder, and that would be E. All right, so basically, even though we put a lot of words, a lot of names to them, just so we're indicating what kind of equation it is. So the name reflects the equation. I hope it's not too bad. All right, so that was the question number 5. Really are a review of those terms. Okay, so I'm gonna move on to section 2. Any questions? Okay, try these assignment. I mean, I did a couple of them, 3 of them out of the 7 question. All right, so today we're working on 10.2. I think I had 5. Maybe I should do it later. So let me pull it back. Two. It's called section 10. Right. All right, let's look at 10.2. We're moving on to vectors. So basically 10.1 introduces two-dimensional coordinate system, and 10.2 are moving on to vectors. How many of you already had like linear algebra classes before? You haven't done linear algebra? So linear algebra. Okay. I am teaching linear algebra next semester. So in linear algebra, we study things are not one-dimensional. So you have multi-dimension, higher dimension quantities. That's when we're using vectors. For the vector, basically is matrix that is in a smaller dimension. Right. So what's the purpose of vector? In mathematics, we normally study numbers. Also be the word direction. Somehow we're change it to a theta. Right, so vectors is a mathematical object that conveys both magnitude and direction information. So far, all the quantities or numbers that we study has value. So they have magnitude, and they don't normally carry information about their angle. But vector is one that allows you to combine with numerical representation, but conveys angular information, conveys direction information. Okay, so let's start with definition. A vector is a directed line segment. This is a purely algebraic notion. So we're defining it using a little bit geometric notion. We use a little bit of geometry when we determine the term, and then we are slowly moving on using algebra to represent the geometric figure. So a vector is a directed line segment. So you have to have because they are directed line segment. So you have to have an initial point and a terminal point. Notation wise, let's say the initial point is P and the ending point is Q. We use PQ with an arrow on top of it to represent the vector PQ. So giving the initial point and Q being the terminal point. So after determining initial point and terminal point, now at least we have a direction. So vector PQ and vector QP are 2 different vectors or opposite vectors that we see. So once you identify the vector, sometimes we use small letters to say vector V. Okay, so that the direction is not as clear about initial point and terminal point, but then just make it short. So use one single letter to represent the vector, and then you probably have to provide more information as you are writing it out. Now, magnitude of the vector PQ is called is also called the length of the vector PQ or the norm. So basically the word magnitude, length, norm about a vector, they're basically the same thing. You really finding the distance between point P and Q. So the magnitude of PQ is really the distance from point P to point Q. And so that's basically the magnitude. Like we said, a vector convey magnitude and direction. And so you may have two different vector and they look different, but then as long as they have the same magnitude, same direction, they're being assumed to be the same vector. All right. So for example, this. So you can see in the picture, we have vector PQ from P to Q and vector RS. Okay, so you can see how these two being parallel. So they're parallel, that's why we can how they're in the same direction. Basically is east, right? Northeast, slightly it's to the east, slightly to the north. About the same direction in these two vector, and roughly they're the same length as well. Distance from initial point to terminal point, the distance seems to be the same. So these two vectors are what we call equivalent vector. Even though they start from a different point, they ended at a different point, but they are equivalent vector, same vector. All right, go back a little bit about the dimension of the vectors. We use this notation to represent R2, and that's a collection of all the two-dimensional vectors. The three-dimensional vector, we use R3, which that's curl R with RQ. It looks like RQ, but it's a three-dimensional vector, the set of all three-dimensional vectors, or a set of all vectors in space. So we're trying to, this section, we try to keep going back and forth between two-dimensional vector, three-dimensional vector, two-dimensional vector, three-dimensional vector. The two-dimensional vector are easier because we can visually graph it and talk about it. The calculation and graph kind of go hand in hand, but the three-dimensional vector, we probably rely on number more than the image because the three-dimensional image are just to make a point that we cannot exactly draw it in three dimensions. So our drawing is mostly figure speaking, illustrative purpose instead of calculation purpose. All right, so let's look at how do we represent the vector using number. Actually, we're representing the vector using what people call component form. And this is how do we represent vector in linear algebra. So in higher level math, almost all geometric figure, we eventually will want to find a way to numerically describe them. And so basically vector so far, we're talking about vector PQ, but where is the vector PQ? What was its initial point? What was its terminal point? To really know it well and explain it well, we have to put a number. So let's start with two-dimensional vector. So a two-dimensional vector in R2, we will identify its terminal point and initial point. Let's say to make it easy, we made all these vectors start from 0, 0. So initial point is 0, 0. Let's say terminal point is point AB, and then the vector will be AB. But we use a little pointing bracket to indicate that was a vector. This is the point. All right, the difference between a vector and a point is a point has no it has no area and has no size, has no length. A point only represents the location, but a vector, it has length, it has direction, it has size. So vector and point is different, and that's why we try to differentiate in the notation. But then different book may not be considered the same. So then let's try to find just say most books are following this way. But some books may be a little bit different. So we have AB and 0, 0. AB is a terminal point, the 0, 0 initial point, the vector AB. Another way to represent vector, I think we do this later as well. This is a horizontal vector. We do A, and then B. Okay, now sometimes we can actually also represent vectors as this. We can go A, B. You can write into a vertical vector instead of horizontal vector. And in linear algebra, we kind of differentiate the row vector from column vector. A, B, the one on the screen is a horizontal vector. We say there's how many rows? There's only one row. And how many columns? You can think of it as two different columns. So it's one times two. That's the dimension of the, if you think of it as a matrix. Now, if it's a vertical vector, you write A on top of B. In this case, you got two rows, one column. So it's 2 times 1 as far as the dimension. But realize they essentially represent the same thing. You write a vertical or horizontal, it's a vector with 2 components. The first component is A, second component is B. Similar idea with a 3-dimensional vector. If you start with 0, 0, 0 and ended at a point A, B, C, the vector will be vector A, B, C. Okay. So this is just to make it simple. So the initial point is all 0, 0, 0. But it could be representing vector that's not starting from 0, 0. Let me try to turn this off. Turn this off. Settings. Anyway, so those are the what we call the representation in component form. Any questions? Okay, with that, last one, let's talk about what if we're not starting from 0, 0. Supposing the initial point P is x1, y1, which is a point, and the ending point is x2, y2. So what was the vector? The vector PQ will be, the first component is x2 minus x1, the second component is y2 minus y1. Are we okay? And that was just very hypothetically speaking, and we should try a couple of examples just to get a better idea of how it look like. Maybe I'll use the homework as a way to illustrate. This is 10.2. 10.2 is vectors, introduction of vectors. I'll make sure that it is visible on your side to reassign it. Now, once we do this, so we need to that's longer. So let's say some example of vectors. All right, these are vector summation, vector subtraction, this one. All right, so this is a 3-dimensional vector starting with A. Initial point is A, terminal point is B. These are 3-dimensional point. A is -5, 0, 2. So it's a point in space. And then B is 1, 7, -3. So that's also another point in space. Vector AB represents starting from A and then at B. So how do we represent it? Again, we use this bracket. We start with this kind of bracket. It's on top of the comma key on your keyboard. So the initial point, you're going to have n terminal point minus initial point. In this case, is 1 minus -5. 1 minus -5 would be 6. The second component is 7 minus 0. So we have 7. The last component is -3. Always take the terminal one, this initial one. -3 minus 2, which is -5. And we end it with a pointy bracket. And that's essentially how you represent a vector on webwork. Any question? So then you can see this is how you find the component of a vector when the initial point and terminal point are given. We can calculate the x component, the y component, and the z component of the vector. Any question? Right, let's start with that, and then let's look at other situation. So this kind of section has a lot of graphing. practice so we understand those vector better. And there's maybe also a couple graphing homework, but later on graphing would not be highly on top of the priority, but you can occasionally see how vector are being graphed, so we understand it. So this start with two of the two-dimensional example and moving on to a three-dimensional example. To start with a two-dimensional example. So the first question, I don't have the answer built in the file. That was a while ago earlier. So this one is to sketch the vector v2, -1, starting from p3, 2. So the question had two things. The point P is a point, we think that's a point 3, 2, but the V is vector, meaning that this vector V gotta have initial point and terminal point, and we don't know the terminal point. We only have the initial point. It says to start at P3, 2. Okay, so what do we do? Let's graph. It did say sketch this. So we start with 3, 2. So we go 3, 1, 2, 3 on the x-axis. Again, two-dimensional, it's possible to graph it. So 3, 2, and we find out the point 3, 2 right here. That's point P, which is 3, 2. All right, we're gonna start from here and then really try to do the vector V. Now the V says 2, -1. That's the vector. The 2 means that we will go 2 units to the right, right? So we're gonna move 2 units to the right, and then -1 is indicating a vertical movement of 1 unit down. Okay, so then the vector look like this. So we're gonna go visualize. So we go 1, 2, and then 1 here. So the vector start from P and then here. So that's vector V2, 1, 2, -1. V equal to 2, -1. So 2 is 2 units bigger in the x direction. And -1 means 1 unit down in the y direction. That's our vector V in the picture. Any question? Right, so that's the sketching part. Sketch the V starting from P and then find the magnitude. About how do we find the magnitude? Magnitude of vector is really the distance, right? It's the distance between 2 points. In two-dimensional, how do we find distance between 2 points? We would, that's the vector V, right? You're going to find V. Magnitude, we use 2 vertical lines. That's magnitude of V notation. Magnitude of V equal to really is distance that we see in here. You see, this is 2 units. That was 1 unit. So essentially, we move 2 units to the right and 1 unit down. So the vertical distance is 1, horizontal distance is 2. The total distance or total length of the vector, it will follow Pythagorean theorem, right? So you do 2 square plus 1 square, add it together and take square roots. So this answer is square root of 2 square plus 1 square. Basically, it's 2 square plus 1 square equal to the magnitude square. So that's why the magnitude is square root of 5. So this ended the first question. Any questions?
Is that the notation for magnitude?
Yeah, that's the notation for the magnitude of the vector. At least in this book. Any questions? All right, so you can see to answer this question, you gotta understand how to visualize a vector. When you write the component is 2, -1. How do we understand the 2 being a horizontal movement and the -1 being a vertical movement? To kind of understand the image of the vector once we see the number there. So let's look at the second question. is to find the component form of the vector W, whose initial point is -3, -2, and the terminal point is -1 and 2. So this is a second question. It's a different question. So C. So you can see I'm trying to understand it from both the algebraic way and also the geometric way. So this is a question asking us to find the vector with known the initial point and terminal point. There's in the second question, there's no drawing involved, right? Just finding the component, right? So it will be the same thing that we did with the homework. So calculation will be, I tend to like to write it as starting from R and then with S as vector RS, which equal to the initial point is the X value is -3, for the S is -1. To find the component, the X component, we take the X value from terminal point minus initial point. So it's -1 minus -3. You have to write it. But then normally with subtraction of the negative number, we turn that into a positive number. Then the Y component is the Y value minus the Y value. So terminal Y value minus the initial value, so -2. 2 minus -2. Again, 2 negative, you would turn that negative minus negative to a positive. So that's the calculation part of it. And we combine them into the first component is 2, the second component is 4. So that's vector form. And we can actually draw it to say that the X value and Y value. Well, normally we put the little arrow on top of the notation. So to make it look like a vector RS, we put a little arrow on top of it. Are you okay? So you can see X value increased from -3 to -1, increased by 2. The Y value increased from -2 to +2, to Y value increased by 4. So you can kind of tell what the calculation, what the component actually means. When both components of the vector are positive, it's indicating this vector is increasing the X value and also increasing the Y value. That's the answer for the second example. Any questions? Right, let's try the last question on example. Sketch the vector U2 -1 starting at the point 1, 1 and find its magnitude. Okay. Not only with the three-dimensional graph, I always feel like, hey, we gotta be more time consuming, got to be more careful with how we draw it. So first we will need our axis system. We'll have our X value, the Y value, and this might have it, the Z value. So we got, this is the X, the Y, and the Z. Okay, so number one, it says here we start with point starting. It's point Q. Point is at point Q. So we're gonna draw the Q111. And how do we draw it? We will find a 1 on the x-axis and then find a 1 on the y-axis. And with these two joints, the 1 on the x, 1 on the y. So this point is what we call, that's the 110, the 1 for x, 1 for y, and 0 for z, right? And then now we want to find the z value being a 1. So this is z, and so this is going to increase that much. How do we do it nicely? Draw parallel. Is parallel to the y-axis, and this is parallel to the z-axis, and this is parallel to the bottom one. And this parallel to the x-axis, and this is parallel to the z-axis. So finally, we find the point. This one. Okay, so this is a. Yes, I should make it maybe a visible circle. So that's the point 111, that's the point P. Are we okay? Right, so starting from the initial point, the question says we want to draw the vector U. So we are increasing the x component by 2. So our terminal point, x is gonna go up 2 units, so that's 1, right? 2, 3. X go up by 2 units, all right, and then the y go down 1 unit. So the y was 1 here, right? 1, 1, 1. And we're gonna go down 1, which we'll get here from starting from 1 and then minus 1, we're gonna get 0 here. So then y equal to 0, x equal to 3 is here. And then let's say z equal to 3. So this is equal to 1, right? And I'm going to go up 3. So it's 1, 2, 3, 3 unit up. And finally, we're going to use lines. Parallel to the x-axis. This is parallel to the z-axis. Makes sense. Okay, so that is the ending point we end. So what was the vector? So the vector would be from the initial point to the terminal point. So I think it would look like. Are we okay? So this is what we have, and then we can see how what's the textbook solution. Right, so this is a solution for 1, 2, 3. Answer for 1 is √5, but the magnitude answer for 2 is actually 2, 4. Answer for, I don't know if it's required to draw that. Answer for number, this is the answer for number 3. So that was Q at 111, and this is a lot more stand out. It actually put the x-axis and the axis in the two-dimensional view. You can see start from Q ending at that point. I think we're not too much off, except our orientation is a little different. I have a x-axis that's slanted instead of horizontal. On this one, the picture looks like the x-axis is almost horizontal, and in our picture, we have our axis this way. I think it's pretty much the same. Yep. So that's visualization vector. All right, let's talk about vector algebra. What do we mean by our vector algebra? That is, we want to do summation, subtraction, multiplication, and division of the vectors. But the thing is, multiplication and division of vectors would be really, really difficult. So instead, we start with multiplying a number into a multiplying vector, or summation of the vector and subtraction of vector. So let's look at 1 and 2. 1 is focused on the two-dimensional case. 3 is focused on the three-dimensional case. So if you have two-dimensional vector u and v, then u plus v, when we add a vector, if you have the component form of both vector u and v, when you add the vector, you're adding the corresponding component. So u plus v has first component u1 plus v1, second component is u2 plus v2. And if you multiply the vector, let's say vector v with a number, all you have to do is multiply the number with individual component. So CV, vector CV is actually CV1 and CV2. That's the component of CV. Sure. And same thing with the three-dimensional case. If you want to have u plus v, all you have to do is add the corresponding component. So then the first component, second component, third component are created using subtraction. Now with multiplication of a number, assuming C is a number, C is a number, a real number, so C can multiply every component of the vector v. So you have the CV1, CV2, CV2 as component of the multiplication of a scalar. It's called a scalar product because the vector is multiplied by a number. This number scale the vector. If the C is bigger than one, it calls the vector to be longer. If C less than one, and the CV1 will call the vector to be smaller. So C was able to scale the vector longer or smaller based on C being bigger than one or smaller than one. Now C if it equal to one, of course CV1 will be the same as V. Any question about these? So summation also including subtraction, when you have U minus V, it's like a V multiplied by -1 and then add the V. So basically subtraction vector is like adding a negative vector. So subtraction vector and summation vector are simplified. As far as the component. Any questions? Okay. So we're gonna look at how visualization works and so now we're gonna do a little bit of drawing to understand how U plus V and U minus V can be quickly understand in this connection of the image. Okay, so we want to sketch both of actually in this question, it didn't see how we want to sketch the vector. So we don't say, where do we start, right? If we don't state the initial point, normally we start with 0, 0. So here we are with the drawing. Initially, we need our axis system. So now we're gonna identify 1, 3. X equal to 1, y equal to 3. So this is point 1, 3. Now the vector 1, 3. Start from 0, 0, right? Point 1, 3. So this is a vector 1, 3. Okay, so a vector is not a point, but a vector is connecting two different points. This is our vector. Start from 0, 0, and then at 1, 3. That's vector 1, 3. But if you start from 1, 3, and ended with 0, 0, it will be opposite. It will be -1, -3. See that? Now this vector is increasing x value by 1 and increasing the y value by 3. Kind of producing a slope of 3. The second vector is vector 2, 1 to find the point 2. 2, 1. So we started connecting it. It's the vector 2, 1. All right, last one, we also want to sketch a vector U plus V. And so first of all, we want to find out what is U plus V. So U plus V is equal to, when we are adding two vectors, we're adding the component. So for U plus V, you add 1 plus 2, the first component is 1 plus 2. The second component is 3 plus 1. Right? If we calculate, finish the calculation, it was 3 and then 4. The third component. So how do we draw U plus V? Again, you can draw a different way. In number 1 is you can draw from 0, 0. So if you draw from 0, 0, then you're gonna end again in that 3x and 4 or y. And then let's try to connect it with, say, arrow. So this is a vector. Any question? All right, and then realize you don't see a lot of relation here, but we can see it by connecting more points. So for example, if we draw the vector, this is the vector V, which is 2, 1, right? Vector V is 2, 1. But maybe you can start drawing the V on top of the 3, 1. So this is a 1, 3. If you draw 2, 1, which means the x value increased by 2 and y value increased by 1, so we'll do this, right? So this is 1, 3. So 1 plus 2, 2 units to the right and 1 unit up, right? Plus 1. Then that's the same as this. So maybe I should use the same color. So this two vectors are identical. Right, so you can draw the vector v as your 0. You can also draw vectors starting from 1, 3. And so these two are parallel, right? They're parallel. They're identical vectors, so they must have the same length as well. Same thing with the vector u. You can also draw the vector u from here to here. You see, we'll have initial point here. So it's really 1, 3 represent horizontally move 1 unit, but then vertically move 3 units. So then from this picture, we realize that this is forming a parallelogram, right? And this two sides, two red sides are parallel, identical in length, and the two gray sides are parallel and also have the same length. It's a parallelogram, right? A parallelogram is formed by two parallel lines, and the lengths on the two opposite sides are equal. So equal length, equal direction. When it's opposite side, that's what happened to a parallelogram. So it turns out the summation of the vector, summation of the two neighbor vector, it is longer. It is a diagonal of the parallelogram, right? So this vector. And this is the one way to look at it. Sometimes we think of the summation vector as the diagonal of the parallelogram formed by these two vectors. Or you can think of it as a triangle. This is a triangular way to triangular parallelogram of the u plus v. Another way, the triangular way is like, so you start with u plus v, so that this is u plus v, right? So it's thinking the vector u and vector v. So this is vector v, actually. This side is vector v, right? And this side is vector u. Now, and then here on the parallelogram is the vector u plus. This is v plus u, because we have u and then v, right? And then so it's u vector plus v vector. On the other side, this is u, and this is a v. So that was a u vector. We used a little error. This is a v vector. V is error. Now then if you do u and then v, so this will be u plus v. So this is v plus u, and this is a u plus v. Either way, they end up having the same vector. Another way to see this is that u plus v, which actually equal v plus u. You can form this triangle, like u and v, which this is u plus v. So when you're adding two vectors, when it's added head to toe, so the ending of u becomes the beginning of v, and it's the total ending of beginning will be the u plus v. So this is another way of looking at u plus v using the triangular. You can do the triangular method, or you can do the parallelogram method to understand the visualization of u plus v. Any question? Just trying to illustrate a little bit geometric, a little geometry of the vector algebra. So that was the answer for u plus v, and then and you can see we fill out the triangle. That was the textbook image of both the summation. Okay. Attitore rule and parallelogram law. Right, this is about how do we do subtraction of vectors. Basically, subtraction of vector is like adding the negative vector. So you can have v multiplied by -1 and then add u. That's essentially how to do u minus v. Calculation-wise, you really just have to subtract the component. So u minus v essentially are going to be 3 minus 1, that's 2, and 1 minus 2, that's -1. So in this case, u minus v is a vector 2, -1. So that's how you subtract vectors. Essentially, the summation or subtraction can all be move into the component mode. You can do a component by component. You do component by component summation. You can also do a component by component subtraction. Any question? And then there's a little picture about how do we do it, a subtraction of vector using the image. Okay, so here we have two vectors. This is a u vector. This is a v vector. So how do we do u minus v? Basically, you want to have if it's u minus v, then u should be the terminal point. The terminal point of u is the terminal point, and then terminal point of v is the initial point. So u minus v have to have initial point, terminal point. It will start from the terminal point of v, ended at the terminal point of u. That's the u minus v. So we have formed a triangle, again, using the triangle method to do subtraction of vectors. But summation is head to toe, but subtraction of vectors is toe to toe, end to end connection. So we connect the ending of both u and v to create a u minus v. And this is when you multiply vector by a number. The vector 2, 1 is move 2 units to the right, 1 unit up. That's vector v. But if you multiply v by 2, then 2 times 2 is 4. 2 times 1 was 2. So it's vector 4, 2. So what's vector 4, 2? It would be horizontal move to the 4 unit to the right, and then 2 unit up. So you can see vector 2v in the same image. So basically, you multiply vector by 2 is like having that vector twice as long along the same direction. Any question? Multiply vector by number. And this is property for all the algebra operation that we had so far. So far, we only have multiplying a number and summation. Summation of vectors follow the number series with numbers. So if you add two numbers, then a plus b equals z plus a. Same thing with vector, u plus v is equal to v plus u. The second one is associative property. If you add 3 numbers, it doesn't matter which 2 numbers you add first, the summation will be the same. So if you add 3 vectors, then u plus v first and then plus w is the same as adding v and w and then add u, so summation. This is the associative property. So associate 2 at a time, because according to summation, normally we add 2 at a time. So this is saying adding 3 altogether, we have the same answer. Number 3 saying that 0 is the additive unit. So if you add a 0, adding 0 is the smallest summation. So add a 0 to a vector. This is 0 vector representing 0, 0, 0. Every component is 0. It's the 0 vector. 0 vector is not saying it's the same as 0 number. Number doesn't have a component. The number has a number 0 and we have the 0. But 0 vector, depending on which dimension, it has dimensions. So has its own component. So vector v plus vector 0, 0 vector equals vector v. If vector multiplied by a multiplication number, you can multiply these number 1 by 1. And it will be the same. The number 5 is distributive property. If you have a number multiplied by summation of 2 vectors, then the number can be distributed to each component, to each vector, and then you can have c times u plus v equals cu plus cv. The number 6 is distributive property on the number part. So if you have a vector multiply summation of these 2 numbers, then you can have the first number times v, second number times v, and then work on the operation of the vector summation. Number 7 says if you have a vector that's not 0, possibly multiply with number 0, you will end up having a 0 vector. Notice that they're not the same, we're just making it into a vector form in this. So number multiply any vector equal to the 0 vector. Number 8 is saying that if you multiply a number with vector's magnitude actually equal to the original magnitude of the vector multiplied by the x value c. Last one saying if the magnitude of vector equal to 0, then this vector has to be a 0 vector. Any question? That's, we will talk about property of a certain operation whenever we learn. So later we're gonna talk about dot product of vectors, and then we have a bunch of property of the dot product. Just like right now, we have summation of vectors, now we have property of summation. Yes,
I know in physics we use the variables of I, J, and K. Do we also use them?
yes, we do, yes. So vector I represents the vector 0, 1, 0, 0. It's yeah, in physics, we have some unit vector, like a vector I, the little arrow on top of it. I represents vector 1, 0, 0. So having that just made it easy to write about it. And then vector J is a unit vector in the y direction. So it's really the 0, 1, 0. So that's J. And then vector K representing unit vector in the z direction. So it's really 0, 0, 1. That's the vector that it represents. So which provide a component form, a vector form of all the components. For example, if you have the vector, like say 2, 1, 5, and you would write this is actually 2i plus j plus 5k. So then any vector can be written as a linear combination of the IJK. So essentially the coefficient of IJK are the component that's 2, 1, 5. So that's the component form, this is vector form, but they're actually representing the same. The IJK are the special vector and when we talk about vectors. So it has IJK itself already indicated certain direction. So we need to hold unit vector. So occasionally we want to turn a vector into a unit vector. What's a unit vector? Kind of like a unit circle. Unit circle is a circle that radius equal to 1. A unit vector is a vector that has magnitude equal to 1. So it's a vector that has length 1. What we call unit vector. So that means that all vector, many vector that has magnitude equal to 1. And so how do we calculate magnitude? It would be square root of the first component square plus second component square. Basically, all the vector that has magnitude 1 would live in a unit circle. So for example, let's say we get a vector earlier, we have 0, maybe 1, 3. Okay, so what's magnitude of u? Magnitude of u vector 2 square root of 1 square plus 3 square equal to 10. Okay, so magnitude of u in this case is doesn't equal to 1. That's what we say u is not a unit vector. We could turn it into a unit vector. So maybe we can say v equal to, we can divide the component by the magnitude, such as 1 over 10 for the first component and 3 over 10 as our second component. So what happened now is that every component is now divided by its magnitude. This time, if you square this plus square this, it will equal to 1. So now it's a unit vector. Right, so for the one that's not unit vector, we could turn it into a unit vector by divide every component with the magnitude. Another thing to look at is that when you have a vector 1, 3, so this is a 1, so it's 1, 2, 3, we're at here. So the length is 10, then you have a vector that look like this. Okay. Now with this division there is we are forcing the length to become smaller. We divide it. So we're like drawing a circle of radius 1. And then what happened here is this vector Okay, that's the vector V, that's a unit vector. So we are still going in the same direction, I mean, the ratio between X and Y is still 3:1, right? So it's Y over X is 3/1. The tangent of the angle is 3/1. Just like this is 3/1, this tangent is 3/1. It's the same angle, but then we're shortening it, we're making it a radius equal to 1, or magnitude equal to 1 when you're forcing it to live in a unit circle. Are we okay? So that is this one. This red vector is the vector 1/10 and 3/10. And all the angles that are in a unit circle have the same. Now, if we call this as angle theta, if this is angle theta, then cosine theta is equal to x over the r, so it's 1/10. So this is actually cosine theta, and then the sine theta will equal to 3/10. So all the vector all the unit vector, if it's in 2 dimension, then the x value is a cosine theta, the y value is cosine theta. And then the theta go around in circle theta from 0 to 2 pi. And kind of cover all the vector in the unit circle or with unit circle. Dimension is more complicated, so we're probably gonna wait for it later, but at least it's workable. And so in the slides that we have vector 1, 3. Now here is a question about finding the unit vector in the direction of V. The magnitude is 10, so the unit vector will be 3/10 and 1/10. So for question 1, we can quickly answer it. Now for question 2, we'll have to find the magnitude. So what should be the magnitude is 1 square plus 2 square plus 3 square, which is 3, right? Root of 1.4 plus 4. So 3, yeah. So the answer for number 2 would be 1/3, 2/3, and 2/3. That's the component for the W. Any questions? Right, the last question, find the vector in the direction of V with magnitude of 5. Now, once you have the magnitude equal to 1, all you have to do is multiply by 5. So for V, V with 3, 1. So the unit vector of it will be 3/10 and 1/10. So to answer number 3, all you have to do is multiply by 5. 5 times U is 5 times 3, 15/10, and then 5/10. That will be the vector that has magnitude 5 exactly. Because one of these vectors has a magnitude equal to 1. And so then this unit vector multiplied by 5 would have magnitude equal to 5. So once you have the unit vector and turning into a magnitude of 5 is easy. Because if you can turn it back to magnitude you want, you can turn it into magnitude of 5. Or you can do this 5. All right, if that's it for today, we'll continue tomorrow. In the meantime, try to get up the homework pace to make sure our homework is done by Thursday. I'll see you tomorrow.